you know, I get the Bohr model, I get the electron configuration, I get the orbital box diagram, but I don't get the energy level diagram, the one I want. And so that's what's happened. And so this is why I'm not, you know, I'm not going to say much more. You should take a look and see it specifically. And you can always Google it too. You know. But we need to move on. Cody, there was a quiz here, so you can get the question off somebody in class. It's going to be take-home. All right, what I want to do is I want to go back to Lewis structures here, because we're doing a Lewis structure lab tomorrow. So we're going to get lots of practice drawing these, but I want to do some examples today. So let's take a look at drawing the Lewis structure for ammonia, or the Lewis diagram. I call them Lewis structures. So what are they doing here? Can you tell me what they're doing here in this step? Okay. Yeah, they're adding the valence electrons. So 5, that N just means that nitrogen is 5 valence electrons. So really it's just 5 plus 3. The 3 comes from what? Yeah, hydrogen each has 1 valence electron, and we have 3 hydrogens, so it gives us a total of 8 valence electrons there. And so we have 8 valence electrons to work with. Why don't we do the core electrons here? Well, we don't show the core electrons. Now there's no charge here, so that's where we're going to stop. If there's a charge here, we have to add additional electrons or remove electrons. Since a hydrogen atom is never central, the nitrogen atom must be central. So where does that come from? Why would we want to put the hydrogen atom in the center? The reason we would want to put the hydrogen atom in the center is because typically the least electronegative element goes in the center. And so hydrogen is less electronegative than nitrogen, so we put it there, except we can't, because hydrogen can only form 1 bond in these structures. And so it's never central. Nitrogen is going to go in the center. And so what they do is they'll draw a skeleton here. This skeleton's so we draw a skeleton like this. Nitrogen bonded to 3 hydrogens. And so how many electrons have we used up? So when I count the electrons, we'll just count it like this. I've used up 2, oh my, 2, 4, 6. I've used up 6 of my 8 electrons. Okay, now I have 2 electrons left over. And the 2 electrons, usually what we do is we put those on what we call the terminal. These hydrogens are terminal atoms. This nitrogen is a central atom. And so normally we try to complete the octets to the terminal atoms first. But hydrogen, does it require an octet? No, it just requires a duet, and the duet is complete. And so after we complete the duet or the octet to the terminal atoms, then we'll put any excess electrons on the central atom. The central atom in this case is nitrogen. And so we have 2 extra electrons, which will just go here. That. And so we end up with this structure here. Now, does nitrogen have an octet? We have to check that. So looking to see if nitrogen has an octet, we look at the total number of electrons around it. This total number would be 2, 4, 6, 8. So we have an octet here. So we're good. The diagram is done. We've used all 8 electrons here. That's ammonia. What are the? Tell me some chemical properties of ammonia. Ammonia is a. You know about ammonia. Ammonia is normally a gas at room temperature. Ammonia gas. It's used in a lot of cleaners. You don't want to mix bleach with ammonia cleaners. Do you know why? Because it could generate toxic gases. Also, potentially, it could create a pressure explosion. not a flame explosion, but a pressure explosion. Why is that? Why would bleach react with ammonia? Ammonia, well, normally when we think about the chemical properties of ammonia, what comes to mind for the chemical properties of ammonia? Let's see if I have. Well, one, redox is one type of reaction, and then acid base is another, and metathesis is yet another. So what are the chemical properties? Let's start off with metathesis. Do you expect any metathesis properties from ammonia? This is going to be just a side, because repetition helps. So just do a little bit of repetition here. Just looking at the chemical properties of ammonia. So first, we'll look at metathesis. Well, there's some physical properties. One, it's a gas. How do I know? I memorized it. Two, it's a colorless gas. How do I just memorize or look it up? It has a distinct odor to it. Ammonia smell. That means its boiling point must be fairly low if it's a gas. And so let's go on to the chemical properties. Let's start with metathesis. Are there any metathesis that you would expect from ammonia? So what were metathesis reactions again? Oh, and those are the driving force, but in a nutshell, what is a metathesis reaction? Single replacement is a redox. Double replacement would be a metathesis. So describe a double replacement to me. AB plus CD. Well, I want you to get away from that kind of thinking, AB plus CD. Metathesis is what? This is something I said repeatedly. Metathesis can be summed up as not a pattern, AB plus CD, but more generally, AB plus CD is too specific because you're going to miss a lot of potential metathesis reactions if you just memorize the AB plus CD pattern. There are going to be a lot of different patterns there. You don't want to memorize every single pattern. There are too many patterns to memorize. And so what's much easier is to come up with a more generalized description of metathesis, which is, the thing is, you can make your life much easier if you do this repetition yourself. You can make it much easier if you just review, whatever, as long as you have notes. If you have notes, then you can review it. If not, then you're just doing it straight from memory. But what helps even doing it straight from memory is to repeat it, because otherwise you forget. I forget a lot of stuff if I don't repeat it. And so we covered metathesis a long time ago, so by now I would have expected you to repeat this so many times that it's drilled into your memory, so you wouldn't have to delay this long. I mean, this is very troublesome for me, thinking, because, you see it's not going to be like this. It's going to be, hyper competitive. You got to watch out. And so it just means having to shift your way. I had to shift too, because I transferred. I was a transfer student from Santa Barbara City College to UCLA. It was a whole eye-opening experience, because I was doing very well at Santa Barbara City College without having to do a tremendous amount of work. But when I went to UCLA, I did a tremendous amount of work, and still I wasn't succeeding initially. I mean, I devoted all my time to study. Because what else? I didn't know anybody around there. It was new. And so what else to do? Just study. All I did was study. It wasn't successful because I didn't study. At least I didn't know how to study at that time, even though I thought I knew how to study. And so anyway, by now it should be like easy. Coding?
With metathesis, like a good example for metathesis on that would be once participates by a gas and sugar reactions. Is that
Well, that's not, okay, can you tell me then? Tell me, metathesis, what is gonna react with?
Water.
You say AB plus CD?
Stronger or weaker acid.
Well, okay, stronger to weaker acid?
Replace, swap or whatever it's added, but I mean, not exactly to the equation, but,
Okay, what would the AB part be here? Tell me what the AB is. A is what? Nitrogen 3 plus? Nitrogen 3 minus? What is the AB? Well, when we do the charges, what would we assign the charge of nitrogen to be? Is it 3 plus or 3 minus? It's 3 minus. We would assign nitrogen. So would we have A is nitrogen 3 minus and B is H plus? Is that our AB? We're going to have 3 of them. They're all the same. Is that our AB? What's our CD? Okay, if I want chemical properties, start listing all the CDs that it's going to react with. Can you do that for me? Because you're using the wrong approach. That approach is you'd have to have a huge amount of information memorized in order to answer that for me, because you'd have to have all the CDs that this AB reacts with here. Do you have that? No, so we used a totally different approach than this pattern thing. You know, I could give you different CDs. Sodium chloride. Would you get a reaction? Then what you do is you keep going down the list. It's kind of a ridiculous way of doing it because it's way too much to do it, but there's a problem here, and the problem is this. What are metathesis reactions in general? What are they called? This should be, hopefully this is in your notes. Metathesis reactions, AKA, are well, the reason I'm saying this is because on the final exam, this chemical properties stuff is going to be a big part of the final exam. Actually, it's going to be all the bonus points are going to be writing reactions. There are going to be a lot of bonus points on the test, about 18 points worth of bonus reactions on there. And so, just because we had that exam a while back ago doesn't mean you can forget about this stuff, because you're going to see it again. Fortunately or unfortunately, you know. Fortunately, if you're good at these, you know, and some people are good at these, but I think a lot of people aren't good. You know, a lot of people bomb the reactions part of the exam on the last test. So this is why I want to go through it for a little bit of repetition. So hopefully you can get a lot of those bonus points that are going to appear on the final exam. And so, but metathesis are favorable, what? Favorable, maybe that's a trigger there. Favorable, did anybody even read the PowerPoint? Probably everybody read the PowerPoint, but everybody forgot it, right? By now. Probably everybody forgot it because it was so long ago. But, and this is why I keep emphasizing, because I did the same thing as a student. You know, I forget everything. And so I didn't remember a lot of that stuff. And then when it came to the final, I was in big trouble. At UCLA, they only had one midterm and one final. If you bomb the midterm, it's all on the final. Hopefully you don't bomb the final too. So I bombed the midterm, and so I had a lot of pressure on the final. Because it was the final that was either going to make or break the class. So this is it. You know, this is the whole goal of metathesis. We want favorable ion combinations. So what is a favorable ion combination? Something that precipitates, precipitation, gas formation, stronger to weaker acid. Is ammonia an ion or a molecule? the molecule. So normally we would think ammonia does not participate in metathesis reactions. Ammonia shouldn't participate. But Cody, what you were saying earlier about ammonia and water, yes, ammonia participates in a secondary way, not in a primary way. I mean, or actually in actually a precursor way. Because what happens is in metathesis, ammonia reacts with water to form a little bit of ammonium and OH minus. And so these are the ions. These ions can participate in metathesis. These ions can participate in metathesis. So what we need to know is we need to know the properties of the ammonium ion. What ions does ammonium like? So all ammonium salts are soluble, so there's no precipitate. And then ammonium is a weak acid. Ammonium's a weak acid. And so, it being a weak acid, it can react with a lot of things. You guys remember this trick to using this chart? Ammonium, will it neutralize ammonia? No, we need a stronger or weaker base than ammonia to react with ammonia. Stronger base. So ammonium will react with all these bases here. However, it won't react with these bases here. There'll be no driving force for that. And so, yeah. So in terms of metathesis, we're going to have the metathesis properties of ammonium and the metathesis properties of hydroxide. Hydroxides will precipitate out most metal cations except for group 1 ammonium and calcium, strontium, barium, but otherwise everything else will precipitate out. So there's a lot of metathesis for hydroxide. Hydroxide is also a powerful base, and so it can neutralize. Hydroxide won't neutralize water. However, hydroxide will neutralize any acid stronger than water, or react with any acid. So it will react with all these acids up here. So those are metathesis. And then after metathesis, we go to acid-base. Well, as far as acid-base goes, what is ammonia? Ammonia itself, this is a amphoteric. It's both an acid and a base. You see ammonia's here, so it's a moderate base. So ammonia can react with any acid that's stronger or weaker than ammonia. Any acid stronger, so it will react with all these acids here that are stronger. It won't react with these acids down here. That's ammonium. Ammonia. Ammonia is also an acid, but when you look at the strength of an acid, it's a very strong acid. No, it's near the bottom. Ammonia is near. And so ammonia needs a base that's stronger than this base or weaker than this base to react. Stronger, so it only reacts with 3 species: oxide, hydride, and this one's called methide, but you don't need to know the name. This is an organic super base. And so yeah, it's acid base, but pretty much it's dominated by it's a weak base, and it's an exceptionally weak acid. And so its acid properties are so weak we don't really worry about it. And so typically we think of ammonia as a weak base. How about its redox properties? Well, as far as redox properties go, do you expect it to be electron rich or electron poor? It's electron rich, you're right. Ammonia, you can burn the stuff. You got to watch out. If you burn ammonia, you can form a lot of toxic gases, toxic compounds. It's electron rich because the nitrogen is -3. That -3 isn't as stable as the -2 on oxygen. So this is more susceptible to attack, ammonia. So those are some of the chemical properties of ammonia.
However, if we just change the structure a little bit, then we'll change the properties. So, for example, ammonia, people get ammonia and ammonium confused all the time, but I can't imagine those being confused because ammonium has totally different chemical properties than ammonia. And so if we look at ammonium is not a weak base. Ammonium is what? A weak acid. And so the thing that stands out, the thing that stands out the most about ammonia is not really the metathesis. Metathesis does. Actually, all three things do stand out, but most people think of ammonia as a weak base. But you better not put it in the fire, and you could actually end up getting some precipitates and other stuff that happen. When people think about ammonium, they think weak acid because it's on the acid chart. Most people look at the acid chart
Quite a few times. They've seen it there. It's a weak acid.
But as far as metathesis goes, anything interesting metathesis-wise? Nothing interesting metathesis. Acid base, yes. Ammonium will react with bases stronger or weaker than ammonia? Stronger. And so it'll react with these. However, it shouldn't react with these that are weaker. How about the redox properties of ammonia?
Redox. Electron rich or electron poor? Electron poor? Whenever we look at redox properties, we have to look at the charges on the individual atoms. Those charges are called oxidation states. And so we look at the oxidation state of the individual atoms. What are the oxidation states? Let me see.
Yeah, it's going to be, what's nitrogen's? -3. Hydrogen? +1. And so is that electron rich or electron poor?
Electron rich. Ammonium and ammonia have the same redox properties. You can burn either one. You can burn ammonia or you can burn ammonium. They're going to burn and create the same kind of nasty, toxic gases. Things like, potential product, if you burn into methane, the potential product is hydrogen cyanide. Is hydrogen cyanide a healthy gas? No, hydrogen cyanide is what they use for years in the gas chamber for San Quentin prison.
But anyway, so we have ammonium here, and the properties. So let's figure out the structure of this. So the first step is nitrogen. How many valence electrons does nitrogen have? 5. And then we have 4 hydrogens. Each hydrogen has how many? 1. So it's 4 times 1. And then we have the charge. It's a +1 charge. A +1 charge means we have an extra electron or we're missing an electron. We're missing an electron, so it's -1 here to indicate that we're missing an electron. So this is 9 minus 1 gives us 8. 8 electrons total. And then we build the structure for this. Well, hydrogen can never go in the center, so nitrogen's got to go in the center, and hydrogen always is terminal. And so the only structure we can come up with is a nitrogen with 4 hydrogens bound to it like this. Okay. And then we look, did we use all 8 electrons? Yes, we used all 8 electrons. And this thing is going to have a positive charge here. A positive charge here. Where does that positive charge come from? You think it comes from the hydrogen, 1H+, right? But the way we think about this, all the hydrogens are the same here. We can't tell the difference between any of the hydrogens. And all the hydrogens are, actually all the hydrogens are +1, the nitrogen is -3. So with the +1 and the -3, that's going to add up to a net charge of plus 1. Plus 1 and minus 3. There's another way we count electrons, and this is going to get confusing here. We count electrons in, or we distribute electrons in 4 ways. The 4 ways. Okay, the first way is the octet/duet. And so let's just look at these 2 examples first. Ammonia versus ammonium. Look at nitrogen here. When we look at the nitrogen, does the nitrogen have an octet in ammonia? Yes. Does the nitrogen have an octet in ammonium? Yes. Since ammonium has a positive charge, we put brackets around. We always put brackets around anything that has a charge and write the net charge out here. Okay, then the hydrogens. All the hydrogens will have a duet, so we double count these. That's a duet, that's a duet, that's a duet. Octet, duet. We're good. And so this is called the octet rule. The octet rule has been satisfied. We always try to get an octet, if possible. Sometimes it's not possible. Sometimes we'll have less, sometimes we'll have more. But we'll try to get an octet. So that checks out. The second way we count is by oxidation state. We count by oxidation state. Why? Why do we count by oxidation state? The reason we always do oxidation states is to understand the redox properties. Not everything can be written in the chart. The chart, would get too long. And so a lot of things, a lot of species, you have to figure out yourself what the redox properties are. How do you figure out yourself what the redox? Well, you figure out the oxidation states. And the oxidation state, the way we count it, and we'll talk about it right now, oxidation state is how we've been counting it. We've been counting it this way. This is why we got nitrogen at -3, hydrogen at +1. That's what we've been doing. But when we do oxidation state by a structure, it's winner takes all. The winner is going to be the more electronegative atom. And so this is how we do oxidation state for we set up a nitrogen versus hydrogen. Which one's more electronegative? Nitrogen. Normally hydrogen has some pull. Normally hydrogen's not so weak, right? But we're going to assume this. When we do winner takes all, we're making an assumption. We're assuming that the bonds are 100% ionic. Ionic. There's no sharing. And so I know that that's not really true because hydrogen will put up a fight, but it's going to lose here. And so hydrogen versus nitrogen, nitrogen wins all the electrons. Hydrogen's left with no electrons. And so this is the way we count the oxidation states. How many electrons does nitrogen end up in this? 8. How many is it supposed to have? How many did it contribute? It contributed only
if we looked at its initial contribution, it only contributed 5. It ends up with 8. It has now 3 extra electrons. Those 3 extra electrons will give it a -3 charge. And so the oxidation state on nitrogen is -3. I'll put that in parentheses here, because that nitrogen has this. Nitrogen has 5 valence, and then it got an extra 3, which gave it 8 electrons. Takes 3. Takes 3 from the hydrogens. And so that means it ends up with a -3, 3 extra electrons, 3 extra negative charges. Electrons. Well, that leaves hydrogen with how many electrons? None. And hydrogen contributed, each hydrogen contributed how many? 1. And so hydrogen ends up short. And so hydrogen's going to get +1. That's oxidation state. Okay, let's do one more example for ammonia. Can you draw the Lewis structure and then do a winner takes all for ammonia? Well, let's draw the Lewis structure. Something like this. And so we do winner takes all. Nitrogen versus hydrogen? Nitrogen wins. In fact, nitrogen is going to take all these. So nitrogen is going to end up with how many electrons? 8. But it only contributed 5, and therefore it has 3 extra. Those 3 extra we indicate with a -3 because 3 extra negative charges. And then the hydrogens are left with none, and so it gets the +1. So this tells us about redox properties. All right, that's 1, 2. This is going to be 3. The next way we count it is by a formal charge. Formal charge is important for acid-base properties and whatnot. Redox we primarily use just for, sometimes we'll use redox for acid-base, but this is a different way of counting it. And so this one's important for acid-base, etc. Lewis structures. We use formal charge a lot. The biggest use that you're going to use it for is to determine the most stable Lewis structures. We want to minimize, minimize. And also acid-base props. With formal charge, we assume 100% covalent bonds. We assume 100% covalent bonds, then this is what we're going to get. For ammonia, like this. Okay, and if we do 100% covalent, then it's 50-50 split. We call this 50-50 split. Not winner takes all, but 50-50 split. Well, a lone pair we don't have to split because a lone pair there's nothing there to split it with. Because a lone pair is going to belong entirely to this nitrogen. However, a bonding pair is going to have to be split down the middle. All 3 bonding
pairs are split down the middle. And so what results is this: half the bonding electrons belong to nitrogen, the other half belong to hydrogen. This is even sharing. And so can you tell me how many electrons nitrogen ends up with? Two? Well, actually, each line represents 2 dots. So it ends up with 5. It ends up with 5. How many did it contribute? 5. It contributed 5. It ends up with 5. It broke even. We call that zero formal charge. Formal charges are circled like this, typically. Whereas oxidation states are typically put in parentheses. So if you see something in parentheses, it's likely oxidation state. If you see something circled like this, it's likely formal charge. And so now these are 2 different charges. That's weird because on one hand, the charge on nitrogen is 0. On the other hand, the charge on nitrogen is -3. Well, is it 0 or is it -3? It's somewhere in between. It's somewhere in between because what we're doing is we're looking at the extremes. We're looking at the extremes of nitrogen being, the nitrogen-hydrogen bond being totally ionic or totally covalent. In reality, this is a polar covalent bond. Polar covalent bond is going to result in a partial charge. So the charge on nitrogen in reality is between 0 and -3. We could figure out what that charge is using quantum mechanics, but we aren't going to, because are you going to be doing any quantum mechanic calculations? No. So what we're going to do is we're just going to say it's going to be some kind of partial charge. It's not going to be the full -3. It's not going to be 0. It's going to be somewhere in between. But you go, well, if it's somewhere in between, why do we need to do the extremes? Well, if we do the extremes, it turns out to be extremely useful, because what we can do is, okay, we can visualize these as being all apples. You know, all apples would be like, if we calculate the oxidation state of every species on here, then we're comparing apples to apples, right? Because we're making the same assumption on everything. And so if we can compare oxidation states to oxidation states, that's comparing apples to apples. We can do formal charges. If we do all formal charges, these are the oranges. So we can compare oranges to oranges. But we cannot compare apples to oranges. We don't do that. And so we don't say, okay, it's -3 here, but the hydrogen is +1 here. We don't mix. We stay consistent. And so these turn out to be extremely useful. Oxidation states are very quick, they're very easy to determine, and they tell us a lot of information about redox. Is it electron rich or electron poor? Formal charge tells us a lot about this Lewis structure and also some acid-base properties, which we'll look at later. But what's the formal charge on hydrogen? Here. Well, hydrogen ends up with how many electrons? 1 electron. How many did it contribute? Initially, it contributed 1, so it broke even. If it breaks even, it's good, it's 0. And so the formal charges on hydrogen are 0. So is the charge on hydrogen 0 or is it +1? Well, the reality is it's somewhere in between, but we're going to use these numbers effectively. And this turns out to be a powerful way of doing things without having to do quantum mechanics. Quantum mechanics, you know, that equation, what was that equation called? Anybody write down the equation of quantum mechanics? Yes. Yeah, it's hard to solve that. And so this is a great alternative to doing that. All right, let's do the same thing for ammonium. What are the formal charges for the ammonium? Okay, try it. Tell me what you get for ammonium. Eventually, you should be able to do these in your head. Can you do this one in your head, or if not, draw it out? Uh-huh.
Are you allowed to have charges on the formal chart, like be positive and negative?
Yeah, positive, negative, +2, -2. We could have different charges depending on what we're dealing with.
So it would be -1 for nitrogen,
It would be -1 for the nitrogen
and that is 0 for
and 0 for the hydrogen. Well, one thing is this. The same thing applies. If you sum up all the oxidation states, it has to equal the net charge. The net charge is +1. We summed up the oxidation states, -3, +1, +1, +1, +1, gave us +1. The same thing with the formal charges. When we sum up the formal charges, they have to equal the net charge. And so yours can't be. Yours can't be because it can't be -1, 0, 0, 0, 0, because that would give us a -1, not a +1. So we gotta fix that somehow. -3. Nitrogen's +1. That's correct. How did you figure that out?
Because nitrogen is -3, but you take half of the bonds and you get 4. You get 4 for the nitrogen.
Okay, that's not the way you do it, though. That's not, because I could give you another example where that calculation would fail. And so there's a different way you figure it out. The different way you figure it out is it's 50-50 split. 50-50 split, 50-50 split, 50-50 split. So you're right, we end up with 4 electrons on nitrogen. Nitrogen ends up with 4 electrons in the structure, but how much did it contribute? It contributed 5, it ends up with 4, which means it came up short. Nitrogen got shortchanged. And so nitrogen got shortchanged, and so it ends up with a deficit of 1 electron, right? +1 is it. We don't usually write the 1, it is plus like that. Does that make sense? This happens, you send the tax. California sends the federal government all this tax money, but how much money does it get in return? So for every dollar it sends to Washington, D.C., do you know how much California gets back? A lot less than $1. Whereas some states, they contribute $1 to Washington, D.C., and they get a lot more than $1 back, And so this is the same kind of thing. Nitrogen contributed 5 electrons. Did it get 5 electrons back? If it got 5 electrons back, then it's break even. If it got more than 5 electrons back, it's got extra. If it got less than 5, well, it's a deficit. So we're in the deficit. How about the hydrogens? They're all 0, because they all end up with 1. They contributed 1. So all the hydrogens are 0. And so we take 0, 0, 0, 0 plus 1, we get the net charge of +1. But look at what's happening. Look at what's happening in terms of the charge. When we do oxidation state, the charge on nitrogen is -3. When we do this, the charge on nitrogen is +1. We can't compare those two numbers. We got to compare oxidation states with oxidation states and formal charge, and they're used for different kinds of analysis on these. But anyway, that's ammonium. Okay, the final way is this. The fourth and final way is by representing these as partial charges. Partial charges is we know that these bonds are polar. You know, these bonds are polar. Polar means it has an asymmetric cloud to it. And which one is going to have a pull, a stronger pull for that cloud of electron density? The nitrogen. And so the partial charge will be delta minus on nitrogen and delta plus on these three oxygens. And that's because the nitrogen is more electronegative and it's going to have a stronger pull for the electron cloud here. The same thing for ammonium, which we'll talk about that in a second. Here, although it gets really weird because it's got a positive formal charge. We'll take a break right now. So it went over time here. Take a break. We'll start up again.